Okay, so who uses a web browser here? Easy question. Yeah? Do you use one on your phone? Yeah? And on a laptop or a desktop device, yeah? They're kind of ubiquitous, aren't they? Like, they're pretty much everywhere. We use them for all sorts of stuff these days. And they're really interesting from a security point of view for a bunch of reasons. Not least because there's loads of stuff that as security people we rely on every day, and if it wasn't for browser development, we'd never have them. So little things like, hello? Screensavers. Don't know what happened there. Little things like bug bounties. Did you know the first bug bounty for a consumer product was for a web browser, the Netscape 2, believe it or not. Little things like transport layer security. Again, Netscape invented transport layer security, or SSL as they called it then. Little things like application sandboxing in consumer operating systems. Not a thing that existed before browsers. Things like WASM, the runtime that we use for WebAssembly. Things like memory safe, both temporally and spatially, systems languages for writing software in. So Rust was built because of browser design. So there's all sorts of stuff that we take for granted every day, even outside of browser land. You know, if we're writing native applications for our phone, we're going to be using a lot of the same technologies as we'd use in a browser, and they came from this world. And so if we look at browsers, both in terms of a product on their own, and in terms of the technology that goes into them and why those things developed, I think they're really interesting. They're really instructive for us when we're building other systems. So before we go any further, I'll introduce myself. I'm Mark. I spent about half of my security career working as a security engineer for one of the browser vendors, and I worked for Mozilla. And I worked on Firefox. And as part of my work on browsers, I did a bit of work in standards. So pretty much every HTTP request any of your device makes will go through stuff that I specified. So I've got my grubby little mitts all over all your internet traffic, and some of the code in a couple of the browsers I worked on as well. So that's not to say that you should believe what I have to say. Obviously, verify any point that I'm making, but I know a little bit about the subject matter. So let's think about a browser from a sort of abstract, let's build a new product point of view. Imagine somebody in your organization comes to you and they say, we're going to build an application in C++, we're going to load a load of untrusted information over the internet, and it's going to have to handle a bunch of different security contexts where we need to make sure they can't observe or interfere with each other. And the input data is really complicated, like there's all sorts of non-trivial grammars that we're using to define these data. And by the way, we want it to be able to execute arbitrary code by design, and it's got to be able to support images and video and audio and fonts and all sorts of stuff, right? Imagine that security review lands on your desk. What are you going to say? Are you going to feel good about this? No. Okay. Not seeing anyone nodding there. Like, if somebody described what a web browser has to do to you as a potential new product, you'd think they were mad. Like, why would you build this thing? It's doing all this stuff intentionally that is just mad, and yet, you know, that's what we've ended up with. And of course, not all of this came in one time. You know, this is the result of 30-odd years of development, and these features have evolved over time, but the place we're in now with a modern browser is incredible in terms of what's shipped. It's incredible in terms of what it achieves from a security perspective. And again, there's loads we can learn from that. So just have a little think about some of these things. Start throwing out the first things that you'd think of as being worrying about this. What's first on your list? Feel free to just shout something out.
Untrusted sources and arbitrary code.
Okay, untrusted sources and arbitrary code, yeah? I'll tell you the thing that makes me most nervous. You know, 30-odd million lines of C++. how many defects per line of code for you to have a very, very bad situation? Yeah. There's all sorts going on here that is really, really, really hard. And it's incredible that the browser vendors can manage this. Now, I mentioned, obviously this has been going on for a very long time, and browser vendors haven't always done a very good job. And one of my favourite web pages is the Wikipedia article on the same origin policy, because it contains a one-sentence horror story. Can you spot the one-sentence horror story? The same origin policy was introduced by Netscape Navigator 2 in 1995, shortly after the introduction of JavaScript. What does that mean about what was possible in a browser between release 2 and 2.02? Any script loaded from any origin can do anything with anything, right? And incidentally, this is after they had introduced SSL. So there was this notion of secure traffic so you could carry out transactions, and they didn't have a security model. They shipped the feature and they're like, oh yeah, we should probably secure this, right? And it's not just the issues that happen by design. If you ship a feature like JavaScript and you don't have a security model, that's one thing. It's quite another if you're dealing with lots and lots of code written in an unsafe language on an unsafe runtime. Okay, and so think about the early days of the web and how awful many of the security vulnerabilities that existed in the browsers that were common at the time. Think about the early versions of Internet Explorer. Terrible, terrible situation from a security point of view. But it improved a lot over time. Now, there's one really interesting thing that I was a little bit involved with in terms of where I was working that is quite instructive in some of the things that we can do and how we can prioritize them and what constraints lead us to make particular decisions. And that was the introduction of Chrome, the Chromium project, and what that meant for the development of Firefox, which is the product that I used to work on. Because when Chrome landed in, 2007-ish, it was free from a lot of the constraints that were plaguing the other browser vendors. You had Microsoft with Internet Explorer, you had Mozilla with Firefox, Apple was shipping Safari with WebKit, and Apple were free of a bunch of constraints that the other people had. But the point I'm trying to make here is that Google, when they started the Chromium project, had a bunch of different constraints. Whereas Firefox had an old code base, it inherited a load from Netscape, so some of the code was really, really old. While it had an older product, while it had existing users, Chrome had a new code base. They forked from WebKit and they were able to do a bunch of stuff with it. They had a new product, they had new users, and most importantly, Chrome didn't really have an add-on ecosystem at the time, right? Firefox had a lot of users that were very, very invested in the customizations that they'd applied, and it meant that a lot of the stuff that was possible in the Chromium code base wasn't possible in the Firefox one. So, for example, Chrome lands in 2007, and out of the box, it's got a massive security innovation. It's got sandboxing, right? They've got this notion of different processes where you've got the main browser process and you've got content processes, and those processes that manage content can be separated from each other, right? So you've got site and origin isolation. And Mozilla couldn't do any of those things. It couldn't do any of those things because Firefox users used their add-ons, they loved them, and they were very, very tightly bound in with the guts of the browser, okay? And so you couldn't separate the processes and you couldn't separate the origins from each other. But one thing that Firefox did have going for it was that the entire front end of the product was already written in a safe language. But the browser engine itself was written in C++, but the browser front end was written in JavaScript. And then over time, Mozilla did some work to, first of all, separate the processes. There's a project called Electrolysis that separated the various processes, the browser into different processes. Following on from that, they were able to implement sandboxing. It actually uses the Chromium sandbox. It's exactly the same code. And then they were able to introduce site and origin isolation. So probably for the past 5 years, there's been decent feature parity in terms of the security architecture between the two products. But then Mozilla did another thing, which was that they doubled down on the safe language thing and said, right, JavaScript's fine for the front end. What about all that really dangerous system code? And that's where Rust came in, and we'll talk about that in a moment. And that's something that Chromium is still sort of thinking about. They announced in January this year that you can now use Rust libraries within Chromium, but the core Chromium codebase is still written in C++, even though Google now use Rust for things like Fuchsia OS and that sort of stuff. Okay, so different constraints give you different opportunities. And the way Google chose to solve the problem they had was through sandboxing and process isolation. So let's have a look at how this works. The technology varies depending on which platform you're using, but common among all of them is that a sandbox achieves two things. The first is that it restricts access to file system resources. So commonly there'll be something like separate users or separate user groups or something to allow you to do that. And you also want to limit interaction with the underlying file system, so system calls and that sort of stuff. The actual implementation is very, very different. On Windows, there are some frankly inspired subversive uses of system internals that allow sandboxing to happen. It's mostly an accident of implementation. It's certainly not by Microsoft's design, but the Windows sandbox is a thing of hackery and engineering beauty, definitely worth looking at. On Linux, you tend to make use of primitives that are exposed by the operating system, and similarly with Mac OS. So, for example, both Chromium and Firefox on Linux have one layer that prevents access to resources. That uses user namespaces on recent versions of the sandbox and recent versions of the kernel. And then you make use of setcomp filter, or setcomp BPF it's sometimes called, which allows you to essentially restrict the use of the system calls that the browser has access to, or that process. But the key point I want to make here is that the technology is only part of the story, right? A sandbox can ensure that you've got the right boundaries. You've got strong primitives for preventing isolated things from getting out, but you need those boundaries in the right place, okay? So let's talk about that in a little bit more detail. There's a really nice thing that came out of the Google documentation on this stuff called the Rule of Two. Has anyone heard of Rule of Two before? Rule of Two is really simple. It says pick two of untrustworthy inputs, unsafe implementation language, and high privilege. Any more than that, and you've got a problem. Okay, so you can have an untrustworthy input and high privilege, but it has to be in a safe language. You know, I'm not going to do all the permutations. You get the idea, right? Now, the constraint that you have in the browser is that most of your existing code base is going to be in C++. So you already know that B is true. So you have no choice. You have to have either trustworthy inputs or you can only have untrustworthy inputs. You can only have unsafe implementation language and one of the others as conditions that you've got, right? So you must separate A and C. You must separate situations where you've got untrustworthy inputs and high privilege. So I'm known for, I think, a couple of things in the security scene. One is for building robots, another is AppSec stuff, and another is that I always have chickens in my demos and slides. So the analogy I'm going to use here is think about your environment and how you're going to protect the stuff that you need to protect. So the naive approach is to say, well, we're just going to sandbox the stuff that we want to protect and everything's going to be fine because, you know, the fox and the crows can't get at the chickens and their eggs and that's all good. Except the problem you've then got is that your chickens can't get at what they need to get at. They can't get at their food and they can't get at their water and you've got a problem. So you can't just put your chickens in a box. Well, what if you put your boundary around the whole field? Well, the chickens can get to their water and they can get to their food, but unfortunately the fox and the crow can get to the chickens, so that doesn't work so well. Think about this in the browser context, and think about what you're protecting and from whom. So you're protecting the origins, the sites that your browser has access to from each other. Those have got to be mutually private and free from interference. You've got to separate the host system from everything that the browser's dealing with, and you need to separate the browser profile from everything that the browser's dealing with as well. And so the way that tends to work is you have a main process It's broker in Chromium speak. It's called the parent process in Firefox speak. And then you have different sandboxes, which might be for different low privilege parts of the browser implementation, or they might be for origin or site processes. And these do the job of taking stuff that's untrusted and potentially in forms that are difficult to deal with safely, and translating them into something that's predictable and safe. Okay, and then you provide a constrained interface between those things and the broker or the parent process. And by doing that, you can make sure that you can satisfy your rule of two in each case. So here we have high privilege and trusted input and an unsafe language. Here we have low privilege and an unsafe language and untrusted input, and same here, so on and so forth. Right. So that's what's going on there. And so the lesson here really is that you've got to think really carefully about your boundaries. You've got to think not only about the technology, but also that you've got the right things in place. Now, I put an asterisk next to an unsafe implementation language earlier on. The reason I put an asterisk next to it is because actually it's a safe runtime that you need. Yeah. So C and C++ running on bare metal is not safe because it's an unsafe language on an unsafe runtime. But there are other ways of meeting the requirement of having safe code. Now, going back to the constraints, Mozilla didn't have the luxury of a clean slate. They couldn't do what Google did with Chromium and just re-architect everything. But what Mozilla saw was that if you can't make fundamental changes, you can still make incremental changes that make a big difference over time. And so what Mozilla did was quite a bold bet. They said, well, we're probably going to have a sandbox in a couple of years' time, and they did. But in the meantime, why don't we start getting rid of the unsafe bits of code in the dangerous bits of attack surface in the browser? And so there was a project that had been started by a Mozilla employee at the time, a chap called Graydon Hoare, in about 2006. Mozilla started sponsorship of this from 2009 and started building an entirely new browser, an experimental browser called Servo, in Rust. And by 2017, bits of that were good enough to start pulling into the Firefox code base. So a stylo, which was the style engine from that Servo browser, made its way into the Firefox code base in 2017. Interestingly, as I said earlier on, Chromium has started to make use of Rust in the Chrome code base as well. Chromium, Chrome, Edge, etc. But one really nice thing about the implementation of Silo in Firefox was that it got rid of huge swathes of C++ code and made it load safer, but that isn't even why they did it, right? The reason why they decided to move the style engine from Servo into Firefox was because there was a really nice innovation, which was that the stylo engine allowed for concurrent styling, parallelism in the styling engine, which was made possible because Rust is not only spatially memory safe, but also temporally memory safe, right? You can write multi-threaded code and have guarantees over the safety of that code, which means that you can make use of concurrency in a way that would be a real problem in C and C++ code. So they actually did that because they wanted the performance and the responsiveness. As a side effect, it eliminated an entire class of security bugs from that part of the code base, which I think is quite cool, and I think a really good lesson that you can learn. But there's another way of getting to safety, and again it comes back to the difference between a safe language and a safe runtime, which is that actually browsers have got a safe way of executing code built in because of that requirement we had at the start of being able to execute untrusted code, right? The JavaScript engine, there are flaws in implementation from time to time, but it's intended to do that job, right? It is built for that use case. And so by making use of technologies that are built on top of the JavaScript environment and the JIT that JavaScript uses, so for example, WASM, you can actually make use of that to do interesting things with your code base. So one thing that Mozilla did was a project called RLBox, which is where you take libraries that you don't know whether or not you can trust. You build them from their unsafe language to a WASM target, and then you run that WASM target within the browser. And then if you've got a bug in that code, it can't own the browser because it's sat in a WASM engine, right? And Firefox actually ships with a bunch of these. There's a delicious irony here, which I'll get to in a moment, but that's a cool thing. So let's move on to recent news. libwebp. Anyone been following that story? Okay. It comes back to the fact that, like, no matter how hard you try with a code base that's written in an unsafe language, you're going to have problems from time to time. Okay. In the last week, we've had two really, really serious issues where some of the best engineers in the world have failed to write safe code. So libwebp is one example. WebP comes from where? Google research, right? Google is a pretty darn good programmers. I know a few of them. They're smart. And then VP8, one of the codecs that ships with WebRTC. Again, it comes from Google. Google is pretty darn smart, right? And if some of the smartest programs in the world can't write C++ code, what hope do the rest of us have? And the answer to that is absolutely none, right? Over time, you're going to have problems. We can take steps to replace the visible attack surface with stuff like Rust, but that's going to take time. And so there's a really, really important thing here around how well you respond to the problems that you have. Okay. And WebP is one example. I'll talk about a VP8 thing in a moment because I heard something this morning which I thought was absolutely incredible and was a good story. Okay. So my delicious irony early on with that RLBox thing, if you go to MDN, which is the Mozilla Developer Network, and you look at WASM, look what library they use to illustrate how cool WASM is. So wouldn't it be cool if they'd actually used a RLBox version of libwebp instead of the native one? They wouldn't have had to do one of their two chem spills last week. I just thought that was quite funny. Like, what are the chances? Because that article's years old. Brilliant. Anyway, the other thing I wanted to talk about was this. Obviously, the browsers were affected by the WebP thing. Electron's affected by the WebP thing as well. Who uses anything that uses Electron? So we've got Visual Studio Code, Signal, WhatsApp, 1Password, Asana, Miro, loads of stuff. Like basically, half of the desktop applications out there these days are using Electron. And Electron is it's a crime against Chromium, is my joke. Let's take Chromium, let's remove half of the security features, and then let's ship it to everyone's desktops without good update mechanisms. And to illustrate this, what I've done is I've deliberately chosen a script here which doesn't give away who I'm not going to shame any individual company, but I updated all of the Electron apps on my laptop yesterday, and then I ran a little script I'd written to pull the Electron version out of the binary. Thinking about the WebP vulnerability, these are the three versions of Electron that are safe from the libwebp flaw, and this is what's installed on my machine. Now, Chrome 83 is ancient, yeah? Only two of these are not vulnerable to the WebP flaw, and only one of them isn't vulnerable to the VP8 flaw. Okay? So again, on horror stories, that's a horror story in one screenshot. Okay. Now, going back to my earlier point, there's always going to be vulnerabilities. You're always going to have problems. And this is kind of the point I want to make about this. When the VP8 flaw was announced, there was a bit of embargo work that went on between the browser vendors and people that consume that library to make sure they've got a response for it. The team working on this at Mozilla were given a reproducible test case in Chromium, and they had to extrapolate whether it was exploitable and what the relevant fix was in Firefox. They did that, they developed a fix, and they'd done an emergency release within 17 hours of hearing about the problem. Okay. How old is Chrome 83? How old is Chrome 100? How old is Chrome 102? This version of Electron is 4 days old and only has one of the two critical vulnerabilities that released this week. So 1 out of the 8 applications isn't vulnerable to libwebp. Okay, so to finish up, hopefully we've learned something. The first thing I hope you learn is that it's possible to fix big problems. I'm presenting this from my browser. I'm glad that it has the same origin policy. It's a shame it was bolted on after the fact when they invented JavaScript, but there have been bigger problems since. The second thing is that a really important part of secure design, secure architecture, is thinking about your boundaries, not just what the boundaries are, but having them in the right places. The next lesson is that incremental changes add up over time. The next is that language choice matters. Please, please, please stop writing safety-critical code in unsafe languages. If you have to write safety-critical code in unsafe languages, please try and find a way of protecting it. Look for aligned incentives. Very often the biggest security wins you get are by riding on someone else's coattails. So if a security win is also a performance win, rewriting this in Rust will make it 10 times faster. It might do that. And finally, don't trust people that ship browsers and don't put in the security work. Electron is a crime against Chromium, and you can quote me on that. So there you go. I'm Mark Goodwin. I talked about browser stuff, and you can find me there. Thank you.